Good day. I'm going to present you the paper entitled On Cyber Vulnerability of Mass, a simulation experiment to counter a rudder controller attack. This paper is written by Dr. Igor Astrov from the Department of Software Science and myself. My name is Sanja Bauk and I'm research professor at the Estonian Maritime Academy. Both of us work at Tallinn University of Technology, which is located in Tallinn in Estonia. I will start this talk with the scope of our paper. So firstly, the paper gives an overview of the research and practical achievements in the field of maritime autonomous service ships, or MAS shortly. The spotlight is on the cybersecurity of the MAS. More precisely, the behavior of the MAS is simulated in the event of supervisory control and data acquisition, or SCADA, hypothetical cyber attack on the MAS rudder controller. We used as a test bed NEMO research autonomous vessel, which is designed and built by the experts at Tallinn University of Technology and the experts from Mindchip startup company here in Tallinn in Estonia. When it comes to the problem, the proportional integral derivative PIT controller and the Kalman filter are deployed as a SCADA cyber attack mitigation tools. The simulation experiments gave insight into the system behavior without and with the Kalman filter in the conditions of cyber intrusion on the input and output signals of the rudder controller. The effect of a cyber attack has been modeled as an arbitrary shaped periodic signal with a sawtooth waveform imposed to the rudder controller system. On the right-hand side, you can see a different ship subsystems that might be a subject of a cyber attacks. In this case, that we analyze steering subsystem of the ship is attacked through the SCADA system. When it comes to the state of the art, we have to emphasize that maritime is somehow lagging behind the aviation, for instance. And we gave here some examples. Only at the level of USA, there is more than 1,400 self-driving vehicles. Also, at the level of the USA only, there is more than 1.5 million registered drones in operation. On the other side, when it comes to maritime, there are only 2 autonomous operational ferry boats and also 2 operational container ships. In figure 3, you can see the first autonomous ferry boat, Falco, which is built by Fina Ferries and Rolls-Royce in 2018. It carries 220 cars and has 3 decks. In figure 4, you can see the first autonomous container ship, Yara Birkeland, developed by Yara Birkeland and Kongsberg in 2021. And it can carry only 120 TEUs, which is negligible small amount of containers in comparison to mega container ships that can carry more than 20,000 TEUs. So we can conclude that maritime is lagging behind in terms of autonomy in comparison to other modes of transportation. Of course, there are some research experiments with autonomous ships which are developed for research purposes and military purposes. So in figure 5, you can see Mayflower, developed by IBM, autonomous vessel for research purposes. Also, we have a Chinese autonomous mothership, which can launch swarm of unmanned aerial surface and underwater vehicles for monitoring and research purposes. We have to mention that US Navy is creating extra large unmanned undersea vehicles and large unmanned surface vessels and so on and so forth. So there are some research attempts and military experiments, but when it comes to commercial use, the number of autonomous vessels is very limited, as I said. I have to say that maritime autonomous surface ships are very vulnerable to cyber attacks. So, malevolent actors may attack SCADA servers, which monitor, control, and analyze MICE devices and processes. The Internet of Things and cloud-based SCADA may cause several security risks, including unwarranted data and information sharing via the Internet, increase in bandwidth overload, latency, etc. Cyber attackers can use the technique known as a privilege escalation to breach SCADA system and obtain unauthorized access. So, in figure 7, you can see different cyber attack vectors on board the ship, but here we put emphasis on SCADA and the possibility for malicious hacker to enter system through SCADA. Simulate a cyber attack, we use a NEMO mass model. And in figure 8, you can see this mass reference system. The control problem for the model of mass is turned here into a control problem by using a rudder angle delta as a control input for controlling the heading angle of the mass C. The transfer function from the input rudder angle delta to the output yaw rate R is obtained as equation 1, while the heading angle C can be calculated by equation 2. The reference for rudder angle delta is 10 degrees for system 1, and it was applied during the maneuver. PIT controllers exist in many forms. One possible implementation is given by equation 3, and it is applied in our experiment. Using simulation software, MATLAB Simulink, we fixed parameters of this PIT controller in optimal manner. In this slide, you can see the Simulink style block diagram of the mass with PIT controller without disturbance. Also, you can see the rudder angle and the heading angle in the conditions when everything is functioning as it should function. But in the case of malicious cyber attack, things can change drastically in the wrong direction. So in this case, we simulated a cyber attack in the form of arbitrary shaped periodic signal having a sawtooth waveform. And this signal is inserted into the input and output parts of the rudder controller. As you can see, rudder angle and heading angle change completely, and this can cause a severe disturbance in terms of optimal heading and navigating of the ship. So the reference for rudder angle was 10 degrees, while the waveform W repeats every 1 second from the start of the simulation and has a maximum amplitude of 0.002, while the waveform V repeats every 1 second from the start of the simulation and has a maximum amplitude of 0.05. With a usage of Kalman filter, we achieved to neutralize this cyber attack and reshape rudder angle and heading angle to the forms that are very close to the initial ones without the cyber attack. So we have to highlight that the Kalman filter matrix gain L is designed so that the continuous stationary Kalman filter, explained by equation 6, produces an optimal estimate XE of vector X. The matrix A, B, C, D and vector L in equation 6 are also calculated through the simulation process and are presented here and in the paper as well. Thanks to this optimal adjustment of Kalman's filter parameters, we had mitigated cyber attack to neutralize it and come back to the initial state without the cyber attack. And let me conclude, we simulated a cyber attack. This involved hypothetical breaking into the mass rudder control system and inserting a malicious noise into it. The control system for mass is designed so that the mass can remain close to the desired cause when exposed to cyber attacks simultaneously on the input and output of the system. This control system contains speed controller and Kalman filter as its main elements and demonstrates high efficiency for the selected maneuver. The simulated cyber attack on a given model of mass will present an important part of the development of machine learning algorithm for the optimal control and exploitation of the actual mass in the future. When it comes to author's contribution, Dr. Igor Astrov set up the simulation environment in MATLAB Simulink and performs analysis and optimizing techniques. On the other side, I carried out the environmental scan and proposed the research objective. This research has been financed by European Commission Horizon 2020 Mary Siberia project. At the end, let me thank you for your attention.